Let's be clear. This is arguably the most controversial battery technology we've seen so far. The Donut Lab solid-state battery. And the level of attention it's getting is no accident. Normally, announcements about revolutionary battery breakthroughs barely make a ripple anymore. Most people have heard these promises before, and frankly, they've been disappointed too many times. But Donut Lab is making claims that stand out. They say this is the world's first solid-state battery to be mass-produced, offering power and lifespan that are, quite literally, close to immortal. And that's exactly why so many people are raising their eyebrows. Because here's the question that doesn't go away. If you truly had the best battery in the world, why would you use it only in electric motorcycles? That choice alone makes many people skeptical. It simply doesn't make much sense. There are other reasons for concern as well. The CEO of Donut Lab has still not disclosed the battery's chemical composition. He has confirmed that it does not contain lithium, yet at the same time the company claims an energy density of up to 400 watt-hours per kilogram, a charging time of just 5 minutes, and a lifespan approaching 200 years, with around 100,000 charge cycles. Those numbers are extraordinary by any standard. In a previous episode, we analyzed Donut Lab's solid-state battery and pointed out several reasons to question its credibility. Many of you were particularly interested in the chemistry behind it. If it's not lithium-based, then why won't the company say what it is? Well, yes, there's a reason behind that, and we're about to talk about it now. So the big question remains, is this truly the holy grail of battery technology, or is it just another familiar story we've seen before in the tech world? In the battery industry, keeping the exact formula secret is completely normal. That's expected. However, refusing to disclose the foundational chemistry, whether the battery is lithium-based, sodium-based, magnesium-based, or aluminum-based, is highly unusual. Even the most secretive battery companies in the world still identify which chemical family their technology belongs to. Doing so doesn't give away trade secrets, but it does help scientists, engineers, and investors understand the real physical limits of the technology. But Donut Lab is a different story. The company's CEO has made just one thing clear. This battery does not use lithium. And that single statement immediately left a lot of industry experts completely stunned. So why is that such a big deal? Because without lithium, there's basically no known chemistry that can deliver specs this insane at the same time. The most jaw-dropping part is the energy density, up to 400 watt-hours per kilogram. That's nearly twice what common LFP batteries offer at around 175 watt-hours per kilogram, and it blows past even Tesla's most advanced 4680 cells, which sit at about 272 watt-hours per kilogram. With energy density this high, an electric car that normally gets 300 miles of range could suddenly jump to 600 miles or more, just like that. And it doesn't stop at capacity. Donut Lab's battery completely redefines fast charging, going from 0 to 100% in just 5 minutes. Even more unbelievable is its lifespan, up to 100,000 charge cycles, which is anywhere from 20 to 100 times longer than today's batteries.
This pack charges from 0 to full in as low as 5 minutes. As low as 5 minutes, and still built for longevity. Donut battery is designed differently. It's designed for 100,000 cycles. Now, that's not just better cycle life. That's an entirely different category.
Do you realize what that actually means? It means this battery could last over 200 years if you charge it once a day. It could let a car drive up to 10 million miles without ever needing a battery replacement. Yeah, that's why we say it's basically almost immortal. And that's still not all. The environmental adaptability of Donut Lab's battery is just as mind-blowing. It can retain over 99% of its capacity, even under extreme conditions, from bone-chilling cold at minus 30 degrees Celsius to scorching heat of over 100 degrees Celsius.
And at minus 30 degrees Celsius, Donut battery retains over 99% of its capacity. And if you push in the opposite direction, heating the cells beyond 100 degrees Celsius, that's 200 Fahrenheit, the result stays the same, over 99% capacity retention.
Okay, these are obviously very impressive claims, except for the fact that this battery has been revealed to not use lithium. Clearly, lithium-free batteries such as sodium-ion, zinc-based, or aluminum-based all share one common trait. Their energy density is significantly lower than that of lithium-ion batteries. They may be cheaper, more durable, or safer, but they simply cannot achieve the high energy levels that Donut Lab is claiming. That's why most batteries in the world today have not completely eliminated lithium. And when a claim runs counter to the entire body of current industry knowledge, the burden of proof does not lie with the skeptic, it lies with the one making the claim. You know, extraordinary claims require extraordinary evidence. Okay, some other viewpoints argue that Donut Lab needs to protect its technology, because if the battery's composition is disclosed too early, it could be copied. However, we have to wonder what the point of protecting the battery's chemical technology is if the battery has already been manufactured and is set to be used in products shipping this quarter. Yeah, competitors could simply reverse engineer Donut Lab's technology as soon as it goes on sale. According to Electrek, they spoke directly with Donut Lab's CEO to clarify the rumors and take a deeper look into this controversial solid-state battery technology. And as expected, the only thing Marco refused to disclose was the battery's chemical composition. However, the CEO of Donut Lab did explain his reasoning. He said that once Verge motorcycles using the solid-state battery start shipping, competitors will inevitably buy the bikes, tear the batteries apart, and figure out how they work. According to Marco, this won't happen for another 10 weeks, and having a first-mover advantage is critical for a breakthrough technology like this. Put more simply, while competitors are still struggling to research the battery and trying to copy it, Donut Lab will have already sold thousands of units and built up its brand. In the high-tech world, especially in batteries and advanced materials, keeping things secret to protect a competitive edge is completely normal. But the problem here is that Donut Lab isn't just withholding details, it's withholding almost the entire scientific foundation of the product. Meanwhile, according to the CEO, Donut Lab's immediate goal in publicly promoting this technology is to attract the attention of original equipment manufacturers. Marco said the company is sending sample battery packs to OEMs under strict non-disclosure agreements, allowing them to independently verify the claims about performance, lifespan, and fast charging capability. According to Electrek, Donut Lab stated, "We are right now shipping demo packs to OEMs under NDAs and under tight disclosures, so that they can test that all of that is true, which serves our business very well better than disclosing the chemistry." In theory, this is a reasonable strategy, but in practice, it still doesn't resolve the core contradiction. If this battery truly achieves almost non-physical specifications, like 400 watt-hours per kilogram, a 5-minute full charge, 100,000 cycles, and no lithium, then simply confirming the underlying chemical system would already constitute a scientific revolution. As far as we know, lithium is used because it enables the highest cell voltage. Cell voltage is critically important for energy density. Unless composite materials, or alloys, are used to boost cell voltage, it is extremely difficult to achieve a meaningful cell voltage. The next red flag appears when Donut Lab claims its battery can fully charge in 5 minutes while still maintaining high energy density. In battery science, fast charging has always been the enemy of lifespan and stability. High current generates heat and induces mechanical and chemical stress on the electrode materials. That's why most electric vehicle batteries today have to limit charging speed, especially as they approach a full charge. Donut Lab, however, claims to have completely solved this trade-off. But once again, there is no publicly available test data, no charge-discharge curves, no thermal measurements, and no verification from an independent laboratory. All we have are words. And then came CES 2026, which should have been the stage for Donut Lab to prove everything. But no working battery cells were on display. There were no batteries charging, no batteries discharging, no instruments measuring power or energy. The only things shown were a module and an empty battery cell casing. For anyone who understands batteries, this was an extremely alarming moment. Because if the battery truly existed, even a single small working cell would have been enough to silence all doubts. So if it's not lithium, what material is Donut Lab using? According to Electrek, it could be amorphous titanium dioxide. Of course, this is only speculation based on the information Electrek has investigated. All available evidence points to Donut Lab having close ties to a Finnish nanotechnology startup called Nordic Nano. Donut Lab invested in Nordic Nano in October 2025, and in the company's article, a statement by Marko Lehtimäki, acting in his role as a board member, is also mentioned. We are excited by the strong expertise and technology within Nordic Nano and the contribution it will make to the next steps in developing our own product strategy in electrified mobility and, in particular, innovative and sustainable battery technology. Accordingly, Nordic Nano is focusing on the nanostructure of amorphous titanium dioxide, which could offer benefits across a wide range of technologies, including batteries. Electrek notes that the nanostructure of amorphous titanium dioxide fully fits the criteria of a miracle product like a solid-state battery. First, it has the potential to help solid-state batteries achieve 100,000 cycles. Traditional solid-state batteries are crystalline like a brick wall and crack when ions rush in. Dr. Buskuti's amorphous titanium dioxide is disordered like a sponge and breathes, allowing it to expand and contract without breaking. Next, the amorphous titanium dioxide nanostructure also allows for solid-state batteries to be charged in 5 minutes. This chemistry stores energy via pseudocapacitance, which is basically like Velcro. Ions stick to the surface almost instantly rather than having to burrow deep inside the material. And finally, the manufacturing Nordic Nano uses a nanofluid printing process for its solar product using the technology. This aligns with Donut Lab's description of a clay-like material that enables an easier manufacturing process. Some call this battery printing, which could explain Donut Lab's ability to bring this to production in record time. Yeah, these are the arguments Electrek puts forward to support the idea that Donut Lab is using an amorphous titanium dioxide nanostructure for its solid-state battery. Of course, in the end, this is still just speculation based on the relationship between the two companies. What we're wondering is this: if this battery really does use titanium, isn't it much heavier and far more expensive than lithium? So how can Donut Lab be so confident that it can produce this battery at a lower cost? And how much would a complete battery pack actually cost? Verge Motorcycles is set to begin delivering motorcycles equipped with this battery in March. Before that, the company also said we would soon see third-party testing of these battery cells, since samples have already been sent to authorized research and scientific centers to verify everything. However, the cells will not be opened up or publicly disclose what's inside. And this very detail continues to fuel controversy. In materials science and battery research, thorough verification is almost inseparable from analyzing the internal structure. Measuring only input-output performance without knowing the underlying chemistry leads many experts to believe that this kind of validation will have very serious limitations. In short, Donut Lab is asking the world to trust the results without being allowed to ask about the cause. They are calling for a few more weeks of patience until independent tests and the first production vehicles appear on the streets. Until then, the entire market and the public can only rely on statements and promises. And the history of the battery industry has shown that many so-called revolutionary batteries have quietly disappeared after their initial period of hype. As skepticism continues to grow, some critics have suggested that Donut Lab may simply be using the story of a breakthrough solid-state battery as a way to attract investor attention. However, Marco Letomaki has directly pushed back against that idea. The CEO of Donut Lab claims that millions of investors are currently trying to get involved with the company, yet in reality, Donut Lab is not in negotiations with anyone. According to Marco, the company has made it clear to potential investors that any discussion about financial terms can only happen after the full disclosure process and technical verification are completed. Marco emphasized that they will not accept any investment until they have proven that their battery cells actually work exactly as they claim. On the surface, that sounds like a very reassuring statement. It paints the picture of a company that is completely confident in its technology, one that is willing to walk away from enormous amounts of money in order to protect its credibility and scientific integrity. But when we place that statement into the real-world context of Donut Lab, more questions begin to emerge. First, as we mentioned in a previous episode, Donut Lab is a very small company. Based on publicly available information, it has only a handful of technical staff, roughly 9 people. And we all know that developing, testing, certifying, and preparing for mass production of batteries, especially solid-state batteries, requires enormous financial resources, often reaching into the hundreds of millions or even billions of dollars. Yet at the same time, Donut Lab claims it has not taken any investment and does not intend to. That naturally leads to a reasonable question. What financial resources are actually supporting the entire process of research, testing, pilot production, and scaling? Second, in the history of the tech industry, it's not unusual for a company to announce a potentially revolutionary product before raising capital. But in most cases, those companies demonstrate a clearly working prototype, provide independently verified test data, or at the very least, disclose part of the scientific foundation behind the technology. With Donut Lab, we have yet to see any of those elements presented in a transparent way. Third, saying we're not raising capital does not mean that investor expectations are not being created. Gaining global attention and seeing the name Donut Lab repeatedly appear across international media already generates enormous value on its own, not just in terms of brand recognition, but also as future negotiating leverage if and when the company eventually decides to raise funds. In other words, even if Donut Lab has not signed a single investment deal, building a technology narrative that is big enough can still provide long-term strategic advantages. So when we step back, the story of Donut Lab's solid-state battery is not just a typical technology debate. It's a real-world test of how we evaluate so-called breakthroughs in the energy sector. On paper, what Donut Lab is claiming is undeniably attractive: extremely high energy density, ultra-fast charging, an almost eternal lifespan, low cost, and no reliance on lithium or rare metals. If all of this turns out to be true, this wouldn't just be an incremental improvement. It would be a full-scale revolution capable of reshaping the entire global battery industry. But here's the core issue. Every scientific revolution requires evidence, not just promises. As of today, Donut Lab has not released independently verified data, has not publicly demonstrated a fully working battery cell, and continues to keep its core chemical foundation completely undisclosed. The display of empty battery shells at CES, the ongoing silence around technical details, and the repeated references to timelines that are always coming soon. All of these are signals that naturally force the scientific community and industry experts to ask hard questions. More importantly, when we compare these claims with the reality of the battery industry, this level of skepticism is entirely reasonable. Industry giants like CATL, Panasonic, LG Energy Solution, Toyota, and Tesla have spent decades researching solid-state batteries, backed by budgets reaching into the hundreds of billions of dollars, and yet, large-scale commercialization has still not happened. Not because these companies lack ambition, but because solid-state batteries are extraordinarily difficult to manufacture, difficult to stabilize, and extremely hard to scale. So, when a small company claims it has overcome all of these barriers in a short period of time, it naturally demands an equally strong level of proof. That doesn't mean Donut Lab is automatically wrong. Technology history is full of breakthroughs that came from very small teams. But that same history also shows us that so-called holy grail batteries fail far more often than they succeed. So at this point, the most reasonable approach is neither blind belief nor outright dismissal. What we need are independent tests, real-world products, and transparent data. Only then can the biggest question finally be answered. Is this truly the first solid-state battery to step out of the lab and into the real world? Or is it simply a technology story being told too early? And that answer, most likely, will arrive in the months ahead.
EV expert Sandy Munro once remarked that solid-state batteries are the kiss of death for gasoline and diesel, meaning they pose a significant threat to Tesla's 4680 batteries. With the superior power of solid-state batteries, Toyota is confident it can regain its lost position from Elon Musk, boasting a range of 700 miles and a full charge in 10 minutes. If these criteria are met, solid-state battery cells will be a major breakthrough. However, solid-state batteries still face a significant issue. So between Tesla's 4680 batteries and Toyota's solid-state batteries, who's going to be king? Tesla is achieving rapid production progress with a 4680 battery, producing around 140,000 cells per day at the Giga Texas facility. Currently, with Toyota's solid-state batteries not yet on the market, the 4680 battery remains the best available exclusively from Tesla, with no worthy competitors to make Elon Musk truly concerned. But let's imagine the scenario when solid-state batteries hit the market. Will the 4680 become overshadowed? Let's compare them now. We think we should still understand the concept of these two batteries first, because that is the root of the problem. We will explain as briefly as possible. First is the solid-state battery. This is still a battery with 4 components: anode, cathode, plastic polymer separator, and electrolyte solution. However, what makes it a breakthrough to be considered the 4680 killer is the transition from a liquid electrolyte solution to a solid electrolyte solution. Liquid electrolyte solution is found in any other lithium-ion battery. That's the knowledge of solid-state batteries. We think you have understood it. Meanwhile, the 4680 battery was first announced by Elon in September of 2020 and set to begin production the following year. The Tesla 4680 battery remains a cylindrical lithium-ion type with a diameter of 46 millimeters and a height of 80 millimeters. The cathode of the 4680 is predominantly nickel, making up 81.6%, with the remaining 20% consisting of lithium and cobalt. The anode uses silicon instead of graphite, and the cell's characteristics indicate very good technical specifications. But that's not all. What makes the 4680 battery even more special is its use of a tabless electrode design, which eliminates the tabs that connect the 2 poles of the battery. This design helps increase energy density, reduce internal resistance, and simplify the manufacturing process. Both batteries are constructed using technologies that significantly impact energy density. Solid-state batteries with solid electrolytes still need to efficiently conduct lithium ions between flexible cathodes and anodes. On the other hand, the 4680 battery features a structural design and composition that swiftly affects the lithium transport process. So, who will win in energy density? There's no denying that the race in modern battery technology is increasingly fierce, with energy density being the foremost factor driving competition. High energy density means batteries can store more energy in the same volume or weight. Therefore, electric vehicles can travel longer distance before needing to recharge. In the Tesla 4680 battery, the energy density has reached 244 to 296 watt-hours a kg, compared to 200 watt-hours per kg in a typical lithium battery, which means it has improved the energy density by more than 20%. Tesla announced that the 4680 battery will increase the range of electric vehicles by 16%, and combined with the cells-to-chassis technology, the packaging technology helps increase the range of vehicles by 14%. Finally, we will have nearly a 30% range improvement. For easy illustration, consider this example. In the case of a Tesla Model 3 with a 75 kilowatt-hour battery pack using traditional LFP batteries, it would typically achieve a range of about 350 miles or 560 kilometers and weighs approximately 4,000 pounds or 1,800 kilograms. However, if this sedan were equipped with a battery pack of the same size but utilizing 4680 cells, it could potentially achieve a range of around 406 miles or 653 kilometers and the weight cut to approximately 3,600 pounds. This means that the 4680 battery can store more energy per unit volume or weight compared to other types of batteries, resulting in longer driving ranges and lower battery weights for electric vehicles. Currently, Tesla is only using the 4680 battery for the Cybertruck, and the performance for this pickup truck is also extremely impressive. So what about the energy density of Toyota's solid-state battery? While Tesla's 4680 battery pack only aims to surpass most of its competitors' electric vehicles in terms of performance, Toyota is determined to have an electric vehicle with a range comparable to internal combustion engine vehicles with solid-state batteries. You know, with these things that haven't been released, whatever the manufacturer announces is assumed to be true. According to our understanding, Toyota plans to increase the energy density of solid-state batteries to more than double the energy density of current lithium batteries by 2025, reaching 450 watt-hours a kg. This advancement would allow for storing more energy with the same weight. If the Japanese automaker achieves this ambition, it means the energy density of solid-state batteries would be 1.8 times higher than that of the 4680. Consequently, it suggests that the driving range of Toyota's electric vehicles using solid-state batteries will increase significantly compared to Tesla's EVs. If you look on the internet, Toyota plans to use solid-state EV batteries with a range of 750 miles, which means 1,200 kilometers. With this range, Toyota is confident that it'll catch up with Tesla in an effort to regain its lost position. Especially, the Japanese electric car manufacturer also wants to prove that Tesla's 4680 battery is not something to be proud of. Most recently, we also received some sources saying that Toyota is also planning to develop solid-state batteries for EVs with a range of up to 923 miles, equivalent to 1,500 kilometers. It's hard to believe, but if this happens, Tesla could be in big trouble. From a scientific perspective, it's evident that solid-state batteries have the potential to dominate the market in the future over Tesla's 4680 battery, mainly due to their significantly superior energy density. However, it's crucial to understand that higher energy density in batteries doesn't necessarily mean faster charging times. So, how do the charge times of the 4680 battery and Toyota's solid-state battery stack up against each other? Regarding charging speed, according to insiders at Toyota, the prototype solid-state battery has a clear advantage over current lithium batteries in terms of charging speed ranging from 0 to 100% in just 15 minutes. Therefore, customer concerns about hours-long charging times may soon be a thing of the past with solid-state batteries. Toyota's promised charging time is nearly comparable to the LFP cells from Shenzhen recently announced by CATL, which boast extremely fast charging speeds. However, in our opinion, Toyota's solid-state batteries have more trouble achieving these charging speeds. While most batteries can be fast charged at least a few times, applying a lot of power is very harsh on them. This is why the trickle chargers found in many people's garages are surprisingly slow. If someone fast charges their battery frequently, the internal structure of the battery tends to fail after a disappointingly short time. All lithium-ion batteries suffer from dendrite formation, but this happens very quickly in solid-state batteries. Dendrites are like branch formations that can spread between batteries' electrodes, causing them to short-circuit. Until now, it was a mystery how soft lithium dendrites could penetrate through the hard layer of the solid electrolyte. To put it simply, frequent fast charging will cause solid-state batteries to short-circuit easily, reducing battery performance faster than a regular lithium battery with a stable charging rate. So is the 4680 Tesla battery better? With a 4680 Tesla battery, we found that the anode and cathode terminals of the 4680 battery use full polarity tabs, which means that the full polarity tabs will greatly increase the path of the current and make it easier for the electrons to move inside the electrons. That makes the internal resistance of the 4680 battery only 1/5 that of the 2170 battery. Therefore, the estimated charging speed of the 4680 battery will be many times faster than a conventional lithium cell. According to the actual test report, it only takes 20 minutes to charge the 400-volt 4680 battery system to 60%. In the case that the 4680 battery is combined with an 800-volt voltage system, the charging speed will be many times faster. Currently, the Cybertruck using the 4680 battery pack achieves a 40-minute charging speed from 10 to 80% with a fairly large battery pack, 123 kilowatt-hours. Previously, in addition to the Cybertruck, a few Tesla Model Ys were also equipped with a 4680 battery pack and provided incredible charging times. One owner drove the SUV to a supercharger station in California when the car was completely out of battery and couldn't move it any further. In just 32 minutes, the car was charged to 80% of its battery capacity via a 250 kilowatt charger. It's undeniable that the charging speed promised by Toyota's solid-state batteries has yet to surpass Tesla's 4680 cells. This could make impatient customers less enthusiastic about waiting for electric vehicle charging times to become more enjoyable. However, that's not the whole story. If you desire a longer battery lifespan and safety, Tesla's 4680 cells have an advantage over solid-state batteries due to their stable charging speed. Toyota's solid-state battery seems to have two pretty good advantages to surpass the 4680 Tesla. Both energy density and charging time are enough to top the entire industry, but in the end, the cost to produce this type of battery is a nightmare for manufacturers, even a factor preventing it from launching on the market. So, why are solid-state batteries so much more expensive than Tesla's 4680 cells? Talking about a not-yet-launched battery technology being more expensive than a widely produced type of battery may seem contradictory at first glance. However, considering the significant delay since the initial mention of solid-state battery development back in 2020, now nearly 5 years ago, it still doesn't exist. From what we understand, solid-state batteries do not completely eliminate lithium. In fact, some research suggests that solid-state batteries can use lithium in amounts that are 5 to 10 times higher than that in 4680 batteries. The price of Toyota's solid-state batteries is estimated to range from $800 per kilowatt hour to $400 per kilowatt hour by 2027. With liquid electrolyte batteries currently costing around $156 a kilowatt hour, that creates a significant manufacturing cost issue. Toyota's solid-state battery is expensive because it's been reported that the battery uses no liquid electrolyte to transfer energy from the cathode to anode, or vice versa. There has to be a solid electrolyte to take its place. Materials for this type of technology are scarce and very expensive. On top of that, there's no standardization material that's used in the manufacturing process, and no standardized process in which they're made. This makes them extremely hard to mass produce. Some estimates put solid-state batteries at 3-4 times the price of traditional lithium-ion batteries. These costs can add up when you're talking about a vehicle that can already cost as much as $200,000 for a top-of-the-line model. Are the savings worth the added mileage and faster charging? That's for the consumer to decide, and presumably they're going to get their chance. Meanwhile, Tesla's 4680 battery, leveraging a production process controlled by Tesla, aims to reduce costs significantly. The company forecasts a 56% reduction in cost per kilowatt hour and a 69% reduction in capital investment per kilowatt hour. Although specific cost details for the 4680 battery are not disclosed, analysts predict current prices ranging from $114 to $170 per kilowatt hour. Elon has set future goals to scale 4680 battery production to 1,000 gigawatt hours per year, with costs potentially dropping to $70 a kilowatt hour, a challenging but ambitious target. Tesla continues to push forward aggressively and has achieved surprising speed in this endeavor. According to Tesla's VP, Lars Moravi, the company expects their 4680 battery cells to become cheaper by the end of the year by reducing the cost to nickel suppliers. Now, for safety, which battery technology is considered safer for electric vehicles? Tesla's 4680 battery is highly regarded for its safety due to several prominent advantages. Firstly, its simple design eliminates tab connections, reducing the risk of short circuits and enhancing system stability. Secondly, the thicker steel shell provides better protection for the battery cells against impacts and vibrations, thereby increasing durability and safety. Finally, the integrated cooling system of the 4680 batteries helps efficiently control temperature, minimizing the risk of combustion. However, this isn't the biggest advantage of the durability that the 4680 battery provides. Perhaps you didn't know, due to its higher mechanical durability, the 4680 battery is better suited for cell-to-chassis technology. Specifically, Tesla has eliminated the battery pack lid on the 4680 cell, increasing space utilization. In terms of manufacturing costs, must mention that after implementing the integrated CTC Plus mold casting technology, it could save 370 parts, reduce vehicle body weight by up to 10%, and lower battery costs per kilowatt hour by 7%. On the other hand, Toyota's solid-state battery technology is also considered a safe battery technology because transitioning from the liquid electrolyte of lithium-ion batteries to a solid electrolyte helps reduce the risk of leakage. In lithium-ion batteries, the liquid electrolyte allows lithium ions to move between the positive and negative electrodes during the charge and discharge cycles. However, like any other liquid, this electrolyte layer is sensitive to temperature changes. You might have seen batteries swell in the middle or even leak some electrolyte fluid. That's really bad. If the electrolyte vaporizes or leaks out, it can create a short circuit between the positive and negative electrodes, potentially leading to fires or explosions. If that starts to happen under your car's floor, you're in for a really bad day. So in summary, Toyota's shift to using solid electrolytes will make electric vehicle safety much less risky. With the initial development of solid-state batteries, Toyota researchers have emphasized maintaining temps between 50 to 60 degrees Celsius for optimal performance, and expect to surpass these figures as they upgrade to more heat-resistant electrolytes. Real-world tests comparing solid-state batteries and lithium-ion batteries of the same volume have shown that solid-state batteries have relatively low flammability and relatively high electrochemical stability. However, as mentioned earlier, solid-state batteries are prone to rapid and more frequent Dendrite formation compared to the 4680 battery, which poses a challenge. Additionally, recent tests have indicated that they can still catch fire when severely crushed or punctured. This means that even with solid-state batteries in electric vehicles, if a serious accident occurs and the battery pack experiences a significant impact, the risk of fire remains present. Tesla's new 4680 battery cell represents a significant advancement. Not only is the cell larger, but its internal structure is also distinct. Meanwhile, solid-state batteries have long been touted as a great application to unlock the potential of electric vehicles. With their lighter weight, higher efficiency, and faster charging times compared to lithium-ion batteries, solid-state technology is being heavily promoted. Toyota alone holds over 1,600 related patents in solid-state battery technology, underscoring their success once again in the laboratory. But how does that become a viable and achievable means? The answer is probably certain. Currently, most car manufacturers have plans to introduce solid-state battery electric vehicles to the market by the end of this decade or later. This leaves ample time for speculation and bold claims without any specific support for them. At this point, most people are aware that electric vehicles are expected to have longer lifespans than traditional internal combustion engine vehicles. Currently, governments require electric vehicles to have warranties of 8 years or 100,000 miles. California's gone further, setting requirements of 10 years or 150,000 miles. Toyota plans to maintain over 90% solid-state battery efficiency after 30 years of use. If this technology can be realized sooner rather than later, the cycle efficiency will exceed Tesla's million-mile battery capacity. Meanwhile, the Tesla 4680 battery is predicted to achieve a lifespan of over 1 million miles, equivalent to 16 years of use if driven an average of 40,000 miles per year, and depending on maintenance levels. We hope this information is accurate. However, this is only a prediction based on initial test data, and actual lifespan may vary depending on several factors. Usage factors such as fast charging, high-speed driving, and harsh climate conditions can reduce battery life. Proper maintenance, including software updates and regular checkups, can help extend battery life. Additionally, environmental factors like extreme temperatures can also impact battery lifespan. The debate between solid-state batteries and Tesla's 4680 will ultimately take some time to get to a final answer. Electric vehicle batteries are complex, and it's still unclear which technology will meet the needs of the market. Some love a battery pack that offers superior performance, but the majority of others prefer cheaper battery packs instead of expensive ones. While the 4680 is the top choice for Tesla and is expected to be applied in many Tesla models in the future, Toyota is still focusing on accelerating the launch of solid-state batteries by 2027 with many promises to change the game. In addition, many other battery technologies such as sodium-ion batteries, LFP, solar batteries also have similar improvements. So, what do you think about the 4680 Tesla battery and the Toyota solid-state battery? Which one will win the race? Drop a comment below.
EV expert Sandy Munro once remarked that solid-state batteries are the kiss of death for gasoline and diesel, as they are the most promising type of battery capable of enabling EVs to reach up to 1,000 miles on a single charge. This also means they pose a serious threat to Tesla's 4680 battery, which is currently considered the best EV battery in the world. With the superior power of solid-state batteries, Toyota, as a pioneer in this technology, is confident it can surpass Tesla. The company boasts a 700-mile range and a full charge time of just 10 minutes. Toyota believes solid-state batteries will be a major breakthrough, making them more mainstream than Tesla's 4680 battery, and that Elon Musk will fall behind if he doesn't get on board with solid-state tech. However, in our opinion, despite their potential, solid-state batteries still face significant challenges. So the question remains, between Tesla's 4680 battery and Toyota's solid-state battery, who will be king? Tesla is rapidly ramping up production of the 4680 battery, currently manufacturing over 500,000 cells per day across its facilities. For now, with Toyota's solid-state battery still not widely available, the 4680 remains the best battery on the market exclusively from Tesla, with no serious competitor yet that truly worries Elon Musk. But that doesn't mean there's no reason for concern. Many other companies are proving strong results with solid-state batteries, including Samsung, Solid Power, and QuantumScape, and Toyota's solid-state battery is no exception. We believe it's important to first understand the basic concepts of these two types of batteries, as that's the root of the issue. We'll try to explain it as briefly as possible. Simply put, every EV battery consists of four main components: an anode, a cathode, a polymer-based separator, and an electrolyte. However, what makes solid-state batteries different from most current battery technologies and potentially revolutionary is that instead of using a liquid electrolyte, they use a solid one. Liquid electrolytes are found in all lithium-ion batteries, including the 4680. So essentially, that one change, the use of a solid electrolyte, completely transforms the nature of the battery. The 4680 battery was first announced by Elon Musk in September 2020, and to date, is only used in the Cybertruck. Fundamentally, the Tesla 4680 is still a cylindrical lithium-ion battery with a diameter of 46 millimeters and a height of 80 millimeters. Its cathode is primarily composed of nickel with 81.6%, the remaining 20% made up of manganese and cobalt. The anode uses silicon instead of graphite, and the cell's characteristics show very strong performance specs. The 4680 battery stands out not only for its optimal size and structure, but also for its innovative tabless design. This design eliminates the traditional tabs that connect the anode and cathode within the battery, offering a range of significant benefits. By doing so, the battery achieves higher energy density, reduced internal resistance, and a simplified manufacturing process, allowing Tesla to lower costs and boost performance. Meanwhile, today's solid-state batteries come in various shapes, including cylindrical, prismatic, pouch, and even thin film types for small devices like earbuds or smartwatches. However, the most common formats are prismatic and pouch cells, which optimize space in EVs and energy storage systems. Solid electrolytes in these batteries are primarily made from three main types of materials: oxides, sulfides, and polymers. So who will win the race for energy density? There's no denying that the competition around energy density is becoming increasingly fierce, with battery technologies constantly evolving to deliver more power in the same volume or weight. Higher energy density means a battery can store more energy, enabling electric vehicles to travel farther on a single charge, an essential factor in expanding EV driving range. The latest generation of Tesla's 4680 battery marks a major leap in energy density, reaching levels of 300 to 350 watt-hours per kilogram, compared to the traditional 2,170 lithium-ion batteries' 260 watt-hours per kilogram. This represents a 15 to 35% improvement in energy storage capacity. Thanks to its dry electrode manufacturing process, the 4680 not only boosts energy density, but also offers exceptional advantages in performance and production cost. According to Tesla, the 4680 battery can increase an EV's driving range by 16% thanks to its high energy density and tabless design, a significant improvement over traditional batteries. When combined with innovations like cell-to-chassis integration and advancements in battery pack design, the range can increase by another 14%, bringing the total range improvement to nearly 30% over conventional battery systems. A clear example of this is the Tesla Model 3. With a 75 kilowatt-hour battery pack, the sedan can reach a range of 363 miles and weighs about 4,000 pounds using traditional LFP batteries. However, with 46,080 cells, the range could increase to 471 miles, while the vehicle's weight drops to around 3,600 pounds. That's a major upgrade not only in range but also in overall performance and weight efficiency. While Tesla's 4680 battery is primarily focused on outperforming competitors in terms of efficiency, especially with its longer range and lighter weight, solid-state batteries come with an even greater ambition: to create electric vehicles with range equal to or even exceeding that of internal combustion engine vehicles. And in fact, this is not such a far-off goal. The energy density of solid-state batteries today is truly impressive. CATL, the world's leading battery manufacturer, has launched a solid-state battery with an energy density of up to 500 watt-hours per kilogram. Samsung reached a similar milestone earlier this year. In the US, Solid Power has made its mark with a solid-state battery based on a sulfide electrolyte, achieving 500 watt-hours per kilogram in a 100 amp-hour cell. This battery offers superior thermal stability and boosts energy storage by 50 to 75% compared to traditional lithium-ion batteries. One of the standout companies in this race is Toyota, as they plan to double the energy density of solid-state batteries compared to current lithium-ion models, aiming for 600 watt-hours per kilogram by 2026. If successful, Toyota's solid-state battery would have twice the energy density of Tesla's 4680, which would mean Toyota's EV range could potentially reach 750 miles, bringing them closer to reclaiming the lead from Tesla. Furthermore, recent sources indicate that Toyota plans to develop solid-state EV batteries with a range of up to 923 miles. If this becomes a reality, Tesla will face a significant challenge. With such outstanding energy density, solid-state batteries clearly have the potential to dominate the electric vehicle market in the future. However, it's important to note that higher energy density doesn't automatically mean faster charging times, an area where Tesla still leads with its fast charging technology and manufacturing processes. So, how's the charging time? When it comes to charging speed, insiders at Toyota say their prototype solid-state battery has a clear advantage over current lithium-based batteries, able to charge from 0 to 80% in just 15 minutes. That means customer concerns about long charging times, sometimes stretching for hours, could soon be a thing of the past. The charging speed Toyota promises is nearly on par with the Shengsing superfast LFP cells from CATL. Solid-state batteries use solid electrolytes made from metal oxides, metal sulfides, or solid polymers. Sulfides, in particular, are softer materials, and this softness plays a key role in allowing lithium ions to move more easily. Oxide-based electrolytes, on the other hand, can handle higher voltages, meaning they can push more ions through the electrolyte for better performance. However, Toyota's solid-state battery faces major challenges in achieving this fast charging speed. One of the biggest issues is dendrite formation, a serious problem that develops much more rapidly in solid-state batteries. Dendrites are branch-like structures that can grow between the battery's electrodes, potentially causing a short circuit. To this day, it remains somewhat of a mystery how soft lithium dendrites can pierce through what should be a hard, solid electrolyte layer. In simple terms, frequent fast charging can make solid-state batteries more prone to short circuits, causing performance degradation faster than conventional lithium batteries, which handle stable charging rates more reliably. So, is Tesla's 4680 battery the better option? With Tesla's 4680 battery, we've observed that both the anode and cathode use full polarity tabs. This design significantly shortens the path of current flow, allowing electrons to move more efficiently through the battery. As a result, the internal resistance of the 4680 battery is only 1/5 that of the 2170 battery. This means the 4680 charges significantly faster than the 2170. According to real-world testing, it takes just 20 minutes to charge the 4680 from 0 to 60%. When paired with an 800-volt electrical architecture, the charging speed improves even further. Currently, the Cybertruck uses 4680 batteries and can charge from 10% to 80% in just 30 minutes, despite having a massive 123 kilowatt-hour battery pack. Before the Cybertruck, some Tesla Model Y vehicles were also equipped with 4680 cells and showed impressive charging speeds. One owner reported driving their SUV to a supercharger station in California with 0 range remaining, and in just 32 minutes, the battery was charged up to 80% using a 250 kilowatt charger. There's no denying that solid-state batteries charge faster than Tesla's 4680. That alone could be enough to convince impatient EV drivers who don't want to wait around. However, that's not the whole story. Now let's talk about safety, because that's the question many people will ask. Which battery is safer for EVs? Tesla's 4680 battery is highly regarded for its safety, thanks to several standout features. First, its simple design eliminates tab connections, reducing the risk of short circuits and improving overall system stability. Second, the thicker steel casing offers better protection for the battery cells against impacts and vibrations, thereby increasing durability and safety. Finally, the 4680 battery's integrated cooling system helps regulate temperature effectively, minimizing the risk of fire or explosion. The clearest evidence of the 4680's safety is seen in Cybertruck accidents, where despite severe vehicle damage, even near total destruction, the trucks rarely catch fire. However, since the 4680 still uses liquid electrolyte, it's not completely safe, especially when compared to solid-state batteries. Solid-state battery technology is praised by experts for its safety, as replacing the liquid electrolyte found in lithium-ion batteries with a solid one significantly reduces the risk of leakage. To put it simply, in lithium-ion batteries, the liquid electrolyte allows lithium ions to move between the positive and negative electrodes during charge and discharge cycles. But like any other liquid, this electrolyte layer is sensitive to temperature fluctuations. You may have seen batteries swell in the middle or even leak some electrolyte fluid, and that's really bad. If the electrolyte evaporates or leaks out, it can cause a short circuit between the positive and negative electrodes, potentially leading to a fire or explosion. If that starts happening underneath your car floor, you're in for a very bad day. So compared to the 4680 battery, solid-state batteries have a slight edge when it comes to safety. Don't get us wrong, both are considered safe, as each type of battery has its own unique design and safety systems to prevent failures. Even solid-state batteries aren't perfectly safe. If you're looking for a longer, lasting, and safer option, Tesla's 4680 battery actually has an advantage over solid-state batteries due to its more stable charging behavior and lower risk of dendrite formation. One of the downsides of solid-state batteries is their relatively short lifespan, and manufacturers are still working to improve the materials. Solid-state batteries still need further development to completely eliminate risks like thermal runaway under extreme conditions, such as temperatures over 300 degrees Celsius, or internal short circuits caused by dendrites. Even so, they pose far fewer risks than current battery technologies, and creating EVs that don't catch fire is a huge win for drivers. Toyota's solid-state batteries appear to have two strong advantages over Tesla's 4680 cells: energy density and charging time, both good enough to potentially lead the entire industry. However, the production cost of these batteries remains a nightmare for manufacturers, and that's one of the biggest obstacles preventing them from hitting the market. According to Toyota, they claim their solid-state batteries will have production costs that are 50% lower. But don't get me wrong, that doesn't mean they'll be 50% cheaper than today's lithium-ion batteries. It simply means they'll be 50% cheaper compared to Toyota's original cost estimates for producing solid-state batteries. As it stands, solid-state batteries can't compete with lithium-ion batteries when it comes to cost. The materials used in solid-state cells are extremely expensive. For example, lithium sulfide, a promising solid electrolyte, can cost 5 to 10 times more than lithium carbonate, not to mention the strict purity requirements for ceramic electrolytes, which further complicate and drive up the cost of manufacturing compared to current battery technologies. To bring solid-state batteries to market, companies must solve not only performance challenges, but also rebuild the entire battery production ecosystem. While Toyota claims it can cut production costs in half, that doesn't mean solid-state batteries will be half the price of current lithium-ion packs. In reality, producing them requires extremely controlled environments, dry rooms, and strict humidity controls, which add significant costs to assembly. The second major barrier is mass production capability. Creating a thin and uniform, solid electrolyte layer is a significant technical challenge. Most major companies like Toyota and QuantumScape have only seen promising results at the lab or prototype stage. A stable, large-scale manufacturing process has yet to be achieved, and any defect during assembly could pose safety risks or severely impact battery performance. The third challenge is durability. Some solid-state battery prototypes currently last only around 1,000 charge cycles, while commercial products are expected to last several thousand. On top of that, there's the issue of dendrites, lithium crystals that can grow through the solid electrolyte and cause short circuits. Even though solid-state batteries are generally considered safer, dendrites remain a major concern, especially when using lithium metal anodes. Finally, material compatibility is another significant hurdle. Not all current cathode materials work well with solid electrolytes. This means companies might need to redesign electrodes or develop entirely new materials, which could lengthen development timelines and increase costs. While solid-state batteries hold massive potential, they still face serious challenges in terms of cost and manufacturability. Meanwhile, Tesla's 4680 battery, as mentioned earlier, is already being produced at scale, with over 500,000 cells reportedly manufactured daily across its facilities. This suggests the production lines for the 4680 are relatively efficient. Currently, Tesla is only using the 4680 in the Cybertruck, and the truck's performance has been genuinely impressive. That said, it's still unclear why Tesla hasn't extended 4680 use to its other vehicle models. What's your take on that? Although Tesla hasn't disclosed the exact production cost of the 4680, analysts estimate the current price ranges between $114 and $170 per kilowatt hour. Elon Musk has stated a future goal of scaling 4680 production up to 1,000 gigawatt hours per year, with costs potentially dropping to $70 per kilowatt hour, an ambitious but bold target. Tesla continues to push aggressively toward this goal and has already achieved an impressive rate of progress. In conclusion, both solid-state batteries and Tesla's 4680 cells are revolutionary technologies that are pushing the EV industry forward. Solid-state batteries, with their superior energy density, fast charging capability, and enhanced safety, have captured the attention of both manufacturers and consumers. This technology is widely seen as the future of EVs, especially because it addresses key safety concerns associated with lithium-ion batteries, such as fires caused by liquid electrolytes. However, high production costs, a lack of standardized raw materials, and complex manufacturing processes remain major hurdles. For now, solid-state batteries are mostly limited to high-end EVs. On the other hand, Tesla's 4680 battery, while not yet reaching the energy density breakthroughs of solid-state tech, stands out as one of the most advanced and practical batteries currently available. Tesla is rapidly scaling up production of the 4680, aiming to lower costs and increase volume, a strategy that helps the company maintain its leadership in the EV market.